Hello. I want to thank PCC and the session organizers for the opportunity to present the rainfall influence on the high impact weather. As a way of introduction, I have on this image that the Menden-Julian oscillation and tropical cyclone showing in the precipitation that presented here. Menden-Julian oscillation is a large-scale precipitating system that forms in Indian Ocean, propagate eastward into Pacific. It has significant influence on downstream weather, global weather, including hurricanes, heat waves, and weather in Seattle. Sometimes it can produce tropical cyclones along the way, and influence like these storms influence Southeast Asia and Australia. Precipitation is a multi-scale process that tend to rain heavily in these small scale and mesoscale convective system shown in the gray here. It can also organize into this large grouping as this large scale dynamic system like MGO and the tropical cyclones. Here I will be talking about the 20-year climatology, describe the MGO precipitation and the global impact, focus on landfalling tropical cyclone on the US. Finally, I will provide an example of looking at flooding from hurricanes, that they're much more complex, more than the rainfall itself, that including storm surge, and also depend on the natural and built environment in each specific region. The data I'll be using is multi-satellite precipitation over the last 20 years, known as TRIM, and some newer one with higher resolution is a CMORPH, iMerge, and also the NOAA high resolution radar and gauge precipitation data only over the US continent. As an example, I will evaluate the model ECMWF subseasonal forecast with this 20-year data as an example. Traditionally, we know how to track precipitation on the smaller scale and the mesoscale. However, what's new here is how to describe this large scale precipitation, tracking them in time. This methodology called LPT has been described in details in these two papers by Kern and Chen recently. In order to track large scale precipitation, we first apply a spatial filter that making sure it's a large scale. Then we track them in time, usually beyond 7 days. That tells you that it's much longer than the traditional synoptic scale. And the MGO lasts much longer, usually beyond 10 days, and eastward propagating to several weeks or months at a time, something like that. So this is example, if you look at the top panel is the instantaneous rain map. As you know, precipitation tend to rain out in these thunderstorms intensively, and the mesoscale convective system. On the other hand, they can also be organized into this large scale group. In this case, is MGO. So when you do spatial filter, you get this contour. Then you track this contour in time after several weeks, and this is a MGO event. So this particular methodology has advantage compared to previous method tracking MGO that can really provide both zonal propagation as well as meridional structures. The reason the meridional structure is important is that sometimes MGO dominant over the equatorial region with large heating, drive global circulation. When they propagate eastward, sometimes they go into high altitude. So where the heating center is, it really is important for downstream weather. If you're interested in weather in Europe, US continent, where the heating center is very important. And our global models tend to have a difficulty to represent these in details. So as way of looking at climatology, now we can look at multi-scale precipitation contribution to this climatology, which is the top. And the lower middle panel shows you the precipitation coming out of the smaller scale, including mesoscale and short-lived synoptic scale systems. And the lower one is a large-scale precipitation. So the smaller systems tend to be dominant ITCZ storm tracks, and the large-scale precipitation are mostly in the Pacific and Indian Ocean warm pool, including Asian monsoon region and South America and East Pacific, some Atlantic. Over the 20 years, we have tracked over 200 MGO events, and they generally start in the equatorial region, shown as these blue dots, and then they end up somewhere east and sometimes a little bit into the subtropics with the red dots. We can also, looking at the total cumulative precipitation contributed by MGO. So as it turned out, over the Indo-Pacific Ocean warm pool region, that MGO contribute 40 to 50% of annual total precipitation in this region. Given that MGO is still relatively rare event, happens several events a year, so the rainfall coming in this region can be really heavy each time they get here. So they cause the flooding events over the maritime continent, like the Indonesia and Malaysia in this region, and northern Australia as well. They have distinct seasonal variability from the boreal summer, mostly interacting with the Asian monsoon region, and then shift to the south during the boreal winter season, influence Australia, northern Australia, and the maritime continent. They propagate somewhat differently over the summer season versus winter season. They also have interesting interannual variability that influence the MGO initiation and rainfall. During the El Nino years, they tend to form in the equatorial region broadly everywhere and propagate toward mostly the West Pacific. In contrast, MGO form mostly over the Indian Ocean during the La Nina year, and don't propagate as far into the West Pacific as La Nina year. This influences precipitation patterns, like the El Nino year that is very different than La Nina year. Most extreme precipitation and the flooding event over the maritime continent happen during the La Nina year. With these precipitation statistics over the 20 years, we now can use that to evaluate model forecast, seasonal, sub-seasonal forecast conducted by the ECMWF over the same 20 years. The left panels are the short-term forecast in few days. The red panels are the sub-seasonal forecast out to 40 days. The top panels are total precipitation area, and the middle panels are the smaller scale, and the lower panels are large scale. So overall model ranges more over the ocean, then have some biases over certain basins. In the large scale sense, that model have a very distinct patterns that, for instance, this more over the monsoonal region and then less in the Indian Ocean. And also the have a negative bias over the Atlantic basin. The positive bias East Pacific. ITCZ going through this subseasonal, this pattern amplifies, and also model had a problem over the Andes as well. For MGO, model mostly have this pattern error that tend to be preferred more over the West Pacific, having difficulty to get MGO initiation over the Indian Ocean. So we use this data to evaluate model forecasts in two different ways. One, we want to know, can model predict the climatology over the 20 years, regardless where they are, or when do they occur exactly, just total numbers. And these are the model lead time from few days to 40 some days. And very nicely surprising to us that model produced very good climatology over the 20 years. Total number of MGO, regardless of lead time, tend to be compared to observation really well. So model has a good energetics and have a good climatology of MGO. However, this is not the case if you want to see if the model can predict MGO at the right time in the right place, and the scale really, really drops. And especially if you want to match the MGO overlapping in time space larger than 50%, the scale is very, very low. So model have a good climatology, but not able to predict exactly the timing and the space. We also want to know whether the precipitation has a trend over the last 20 years. Here we plotted the rain rate PDF, low rain rate, high rain rate, and the change in time. Here's the present. So if you look over the last 20 years since 1998, the mean, which is represented by this black line, has a little trend over the last 20 years. The rain rate, however, tend to have this shift from early years to the recent shift to the higher rain rate in terms of the rainfall distribution. That trend line is represented in this blue from the 1 to 99 percentile. Spatially, these increase in rain rate tend to happen over the ocean in the ITCZ and SPCZ in particular. These results are still very preliminary. We are going to look into this a little more. So now I'm going to look at the tropical cyclone rainfall. First, look at their contribution in the global scale. This paper recently has described this in using the rain gauge data since 1970 to 2014. Globally, tropical cyclone contribute rainfall to the US and Australia and Southeast Asia, in particular, some Europe, not as much. In terms of a percentage, it can be as much as 30 to 50% in Australia and a part of Australia and Southeast Asia. And over the US, it's mostly roughly 10%. For the US, hurricane landfall, rainfall, we have a better data set. So I'm going to use this NOAA data that using blended radar and rain gauge from 2002 to 2019, about 18 years. You can accumulate rainfall for each of these landfall storms. And you can also do the same for the satellite data. We find right away that the data over land looks different. The satellite tend to underestimate the rainfall over land. So we'll trust this radar data set more. So most of these will be derived from there. So these two panels again shows the radar gauge data versus satellite data. As you can see, the radar gauge data shows some of the really interesting hotspot in the Gulf state and the South Florida and the East Seaboard. Less so in the satellite image. Obviously, tropical cyclone rains much more over the water in general. These are the tracks over the last 18 years, storm tracks. In terms of a fraction or contribution of a TC rainfall to the total, this data set shows the US region that can change from anywhere from less than 10% to 15%, some spot close to 20%. The tropical cyclones also have this known decadal variability in addition to interannual variability. We all know about the ENSO, but here I'm going to show you an interesting phenomena that is driven by the NAO, that because the sea level pressure patterns and the strengths. So the positive NAO phase that tend to have a storm track trend more positive as documented in this study, and more in the negative phase over the negative NO phase over the Gulf region. So based on that, we take the recent decade, that is the NO positive phase minus the NAO negative phase, that's the last decade. This pattern shows up in the precipitation climatology more this seaboard, the NAO negative phase over the Gulf region in South Florida, except this one particular storm that happened in this 2017 case, which is defying the climatology pattern, climate pattern, and that's Hurricane Harvey. For that, we wanted to use this example to take a look at how extreme is rainfall in Hurricane Harvey, as we have already heard a lot about it. It depends on how you look at it. So if you examine Harvey's rain rate in terms of millimeter per day, that shows in this left panels here, that compared to another storm that is the another storm, Hurricane Matthew, you probably haven't heard. In fact, Matthew rains more in terms of millimeter per day than Harvey itself. So is the anomaly compared to the daily climatology. They're about 20 to 50 times of the daily rainfall climatology. They're similar. So in that regard, Harvey is not all that special. However, if you look at the storm cumulative total rainfall, which means the storm dropped the rain cumulative over the life cycle of the storm over that region, now Harvey looks very extreme. The total amount of rain accumulation over near Houston area, it gets up to 60 inches. 60 inches, and that's extreme. Because if you compare to, say, annual rain in Seattle, it's only about 37.5 inch annual total. Compared to Houston, that's just shy of a 50. That's one storm can produce much more than a yearly rainfall in these locations. So on the other hand, a typical hurricane, landfall hurricane is more like a Harvey. They rain heavily in terms of a rain rate, but then at the same time, they move a lot faster. So the cumulative rain is somewhere between, say, 10 to 20 inch. Compared to Harvey, Harvey is more extreme. So the difference is a slow propagating storm versus a fast moving storm. So the slow storm produce much more in terms of extreme rainfall. On the other hand, in the history, we have several storms actually close to what Harvey's cumulative rain into somewhere 50 plus inch rain, but it didn't cause as much flooding. So what happens in Harvey? So Harvey, I'm going to show you a model simulation of Harvey by a couple model developed by my research group here. This animation shows you the Harvey tracking along in the Gulf, made a landfall in the South Texas, and then made this wobbling loop back in a very, very slow fashion with the rain. And the color here shows the sea level, water level, mean sea level. The red is the positive sea level. As you can see, when Harvey making landfall, you can see this positive water level that is the storm-induced storm surge. In terms of rainfall, model produces very close to the observed amount of total rain accumulation. And at the same time, model also shows you this perpetual storm surge over multiple days, almost a week. Even though the height of a storm surge is not as extreme as some other storm produces, there's only a few feet of a storm surge, but over many days. So what a storm surge did in this particular case is this perpetual storm surge blocked the rainwater usually drain out to the sea in this region. So that really did not allow the water to drain out. On the other hand, the Houston area also has this overly built environment that made it without a natural drainage. So the rainwater cannot drain naturally into the soil as well in this region. So the three things, rain, storm surge, and bad built environment contributed to this perfect storm, and it caused a historical flooding in this area. So in summary, this 20-year rainfall climatology has provided us a valuable insights in rainfall associated with high impact weather, in particular MGO and tropical cyclones, in terms of their multi-scale variability and extremes. And also, we have shown a new way of tracking large-scale precipitation in MGO. And it also seemed to indicating to us there is a slightly upward trend of a high daily rain rate over this last 20 years, and mostly over the ocean, especially over the ITCZ and SPCZ. So with that, thank you.